So thank you for giving me this opportunity. Let me take this opportunity to wish both Mustansir and Deepak on this occasion of 70th birthday. It's a really great experience to listen to so many talks. So many of your students have done really well. And I hope to interact with you more in future. Okay, let's start. This is the talk. Quantum noise and information scrambling in multi-qubit evolution. So this work has been done with Sakuntala, which after finishing his PhD in IIT Kanpur with me, he now moved to Weizmann. Last 1 year he has been there. This picture is a Borromean ring, which I just downloaded from internet, Wikipedia. It's basically the classical analog of this 3-qubit entangled state. So these 3 qubits are there. So let's say the blue and red are not entangled if the green is absent. Here you can see from the Borromean ring is quite straightforward. All right. So this is the plan. So first I'll speak briefly about many qubit states. Then I'll go ahead describe state evolution. Basically, two different ways you can evolve states, unitarily and non-unitarily, and then come to results, information scrambling. Basically, how quantum correlations spread and tripartite mutual information. Basically, the sign of this tripartite mutual information, if it's negative, would imply that the correlations don't spread. This is customary to give one slide on entanglement. So let us go through this quickly. Almost everybody must have heard about it. So basically you take this combined state of, let's say, this A and B. I've shown it pictorially here. Rho AB is a pure state, let's say, direct product or entangled. Then look at the reduced density matrix of, let's say, part A. So rho A by tracing out B. And then if rho A happens to be a pure state, so entropy of A is 0. This is a von Neumann entropy. And we'll say that A is not entangled with B. If rho A is a mixed state, represents a mixed state, then entropy of A is non-zero and A is entangled with B. So basically the entanglement between A and B, we can characterize by the von Neumann entropy of, let's say, part A. And the other thing is that look, you start from a state psi, AB combined state, and then you do a unitary transformation, which is a product UA times UB. So UA will act only on part A and UB will act on part B. Then you'll get a state phi. So these two states, of course, this is a pure state, this is also pure state, of course, but the entanglement between A and B will be same if you do such a unitary transformation because you have done a product transformation. So it doesn't change. But on the other hand, if A and B have many other subparts, then let's say AI and BJ, the entanglement may not be the same. Now you do a different sort of unit transformation. You start with state psi and do a UAB, which may not be decomposable as a one simple product UA and UB. Then this state phi and state psi will have different entanglement structure. The entanglement in A and B is different in these two states. And also the distribution of entanglement in terms of various parts will be very different. So entanglement in a mixed state is more difficult to understand. Of course, we talked about here in pure states. So now many qubit states basically means that you have, let's say, many spin halves species. So I've labeled them distinct parts, 1, 2, 3, 4, 5 like that. And then let's say this is one of the basis states. The first spin is up and down, down and up and so on and so forth. So like that, many basis states will be there. So a pure state psi with the density matrix of this form, this is a coherent superposition state, will be a linear combination of all possible basis states with some wave function amplitude given for a particular state. And similarly, you can discuss mixed states where you have an incoherent superposition. You basically have a pure state psi1 comes with a probability p1, and state psi2 comes with a probability p2, and so on and so forth. And typically what we study is the physical observables like magnetization, diagonal correlation function, let's say between I and J, SZ, and off-diagonal correlation function, let's say between spins I and J, S plus and S minus. These expectation values are in given state. Let's say it can be a mixed state or a pure state, whatever. And an extension of this that we study quantum correlations, which are slightly different. For instance, entanglement measure, concurrence measure between, let's say, spins I and j is a C here. When it is non-zero, it can be shown for, let's say, at least for the Heisenberg model, that it is a magnitude of the off-diagonal correlation function minus, and the diagonal correlation function comes in the square root here, and also magnetization. So which means that this is not observable, of course, entanglement measure, but it combines diagonal correlation function, off-diagonal correlation function in a very non-trivial way. So it is not intuitive to say whether it is zero or non-zero. For instance, we know that diagonal correlation will be long range, and off-diagonal correlation function can be long range in some systems, for some models. But in many of the ground state of Heisenberg X-phase systems, it is seen that only nearest neighbor quantum correlations are non-zero. For instance, entanglement between nearest neighbor spins is non-zero, and all other pace is zero. So having a long-range correlation functions does not translate to a long-range quantum correlation or entanglement. And similarly, you can study quantum mutual information, which is basically, let's say, between A and P. A is one spin and B is another spin. In terms of the von Neumann entropy, which is basically rho log rho trace with a minus sign, the entropy of A plus entropy of B and minus entropy of AB. So this is a quantum mutual information. It is similar to this concurrence, but not exactly the same. And similarly, tripartite mutual information is in terms of three spins, is defined this way. It is a mutual information between A and B, mutual information between A and C together, and minus the mutual information of A with BC, which can be written in terms of individual entropies like this. So this one, if this is negative, this TMI is negative, means what? The information shared by A with B and C together is larger than the information shared between A and B plus between A and C. So this actually implies information scrambling. Now, one slide of evolution of a quantum system. Basically, when you say evolution of one state goes to another state, so there is a map. So it's a CPTP map, which only means a completely positive trace Poisson map. So rho is the initial state, let's say, goes to rho prime, basically a function n of rho s, which is, let's say, simply u rho u dagger. This is like a unitary evolution. And this is what happens for a closed system. It's a coherent quantum dynamical process that happens. So when you say the rho has changed to rho prime, so there's some process happened, and that is a coherent quantum dynamical process. Similarly, you can also have rho going to rho prime like this. It is E1 rho E1 dagger plus E2 rho E2 dagger. So these are the Krauss operators. They stand for the one given QDP can be given a representation of the cross operators. And there will be many, many different ways of writing cross operators anyway. So this is the open system dynamics. So here a pure state, let's say input state is a pure state, but then here it will be P1 times rho 1 plus P2 times rho 2 and so on and so forth. So which means a pure state can become mixed. All right. So with this definitions on, so what we're going to discuss in this talk is that we'll discuss unity dynamics interrupted by a quantum noise for an instant. So what that means, so the evolution is the following. Start with the density matrix rho at t equals 0. Through a unitary process, it goes to rho t naught. So this is a Hamiltonian evolution. And then something happens instantaneously, which means suddenly it changes from rho t naught to rho t naught prime, which is, let's say, like either this way or this way. So which means it could be a coherent process or it could be incoherent QDP. And then on t naught onwards, again, it will go through unitary U. So basically, the unitary evolution are taken from t to t, 0 to t, is interrupted briefly for an instant by a QDP. And what is the effect of this QDP on various aspects we can study. So we have actually published some work on this, Cycle student myself. So we studied signal propagation from QDP in various contexts, various spin models, background dynamics, both integrable and non-integrable. And then we also studied interference of QDP with quantum state transfer. And we have studied the Loschmidt echo of QDP. That only means that it's an imperfect time reversal. So that is captured by the probability of return to the initial state if you do an imperfect time reversal. So I'm not going to talk about this. What instead I'll talk about is the effect of this noise, quantum noise, on this information scrambling. So these are the various spin models. I'm sure all of you know. Basically, XYZ, XXZ anisotropic Heisenberg model or XY model. And there's another model we have studied, is a kicked Harper model. So kicking is through this. Without kicking, this shouldn't have been there. And basically, it is XY model here with a transverse field, but the field itself is modulated in this fashion. So it is spin conserving, but it can exhibit non-integrable dynamics. So the eigenstates of many of these models are known, but difficult to track the dynamics, and also numerically difficult for more than 20 spins. So we'll mostly look at 20 spins, and also some of the things can be done analytically. And even the state is known, dynamically evolved state is known, computing the reduced density matrix is not that difficult, that straightforward. All right, so now let us come to this. So now this is for the transverse XY model. So Jx and Jy are given here for h around 0.1, h around 1, and h around 10. These are the two figures. So this is the initial state, which is entangled between it has entanglement between first side and second side. All the other rest are on let's say downspin state. Now what you see is that this is the correlation function, off-diagonal correlation function, the real part of that, how it evolves from starting from here. So in time, this is time, and this is this thing. Now the same thing is the diagonal correlation function. So it's straightforward to evaluate. And the same thing, as I said before, the concurrence or the quantum correlations. For instance, this is for the Ising model. So the Ising model, but the state is sigma z eigenstate. So these are the local sigma z eigenstates, and then the model is in terms of sigma x. So though it's Ising model, it has non-trivial dynamics. So
Professor, you have 2 more minutes.
Yeah, so you see that concurrence doesn't, it spreads immediately to all sides. So now I'll go through the slides, these results a little fast because 2 minutes I have to finish. So this is for the Heisenberg model, isotropic. This is the concurrence and mutual information. You can see that starting from the initial state, which is this, first 2 sides are entangled. So the location of the bell pair, you see that initially this is at here, site 1, and then slowly it goes in time in a linear fashion, that's like a light cone structure. So which means there's a spread of correlation with a finite speed. The same thing you can see in other models also. This is for the Harper model, and this is you see that for G, the coupling, the magnetic field strength is large, and then tau is large. It shows uniform, but then the speed becomes dependent on time later. And this is the tripartite mutual information. As I said, negative or non-negative, it matters. So here in this picture, blue is positive. So you can see that various models, anisotropic Ising model, and then below is anisotropic Heisenberg model, and the left is a transverse XY model. You see that there's a patches of in parameter space where in time where it becomes negative. So that means information scrambling, which only means that correlations do not, quantum correlations do not spread consistently to the other parts. Now, quantum noise, as I said, 3 steps. Basically, we use 3 different quantum channels. One is a phase flip quantum channel, and is bit flip quantum channel, and there's a coherent unitary QDP, which are defined like this. And let us see what happens. Okay, so I have exceeded time already, it seems. So what I'll do now, I'll just give you in 1 minute, I'll say. So just look at this. This picture, this is the tripartite mutual information. This is for the Heisenberg model, and this is a change in the entanglement between site 1 and 3, and this is for 1, 2, 3 because I have done a QDP on site 2. As you can see that nowhere there is this red the patches, so which means more or less it doesn't spread. And this is for the Heisenberg model with a different channel. That was a phase. This is bit flip channel. And you can see some small patch here. And this is for the transverse XY model. You see a large region where it is negative. So it has information scrambling. And similarly, this is a different channel. And this is the summary of the things which I have not gone very shown you clearly, but I can say this is a summary. This is a spin model, and this is a sign of TMI without QDP. And whether there's a finite speed of propagation of local correlation. Local correlation means local quantum correlations. So for the Heisenberg model, this spin conserving and integrable is non-negative. And yes, there's a finite speed. And the Ising model, spin conserving, non-conserving, and integrable is negative and also no finite speed. And transverse XY model, of course, there are 2 regions. One is large H, then it is non-negative, and small h is negative. And kicked Harper model is non-negative, and speed is finite. And this is the list of models we have studied with various TMIs, whether the change of sign which actually is different when you use TMI, the QDP. So for the Heisenberg model is without QDP, of course, non-negative, and with QDP, it can be negative, which is incoherent QDP. With coherent QDP, of course, is non-negative. And then for the XY model, without QDP is negative, and incoherent QDP is also negative, and the coherent QDP also negative. So XY model in transverse field for small fields is the case where correlations, quantum correlations do not spread easily, and then QDP also will give the same thing. Whereas transverse XY model, large H is non-negative, and then the moment you have QDP, it can actually become negative. So these are the results we have, and thank you for your attention.
Thank you for this interesting talk. Are there any questions? Okay, so if not, then we should thank Professor